Let's look at the harmonic series. This is the harmonic series. It's the sum of 1 over I, with I going from 1 up to infinity. The question here is this finite or infinite? Now, I know earlier I told you that it was infinite, but I didn't really tell you why. So let's look at that. First thing I want to do is let's just look at the sums here, the partial sums for the first several entries. Obviously, the first partial sum is 1. The second one is 1 plus a half, which is 1.5. I've got a bunch of them in a chart here. If we look at it, it seems to be growing, the partial sum, but it's growing slowly. And that makes good sense because the thing we're adding on every time is 1 over I. So, by the time we're up to, say, 25, it's 0.04 that we're adding on. When you get up to 100, it's 0.01 you're adding on. So the thing that we're adding on, the terms are getting small. But if you look at the partial sums, they seem to be creeping up slowly. Now this is the first 34 partial sums. If we skip ahead to the first 100, 200, and so on, we can see that the partial sums continue to grow, but they're growing really slowly. By the time we add up the first 100,000 terms, we're just at 12.090146 ... So just looking at this, you'd probably guess that it's infinite, but it's growing really slowly. So let's show why it's actually infinite. But what I'm going to do is show that every time the number of terms doubles, it increases by at least a half. The sum increases by at least a half. So if we look at this chart again, if we start out with just one term, the partial sum is 1. Two terms, the partial sum is 1.5. So it got bigger by a half. If we go from 2 terms to 4, it goes from 1.5 to 2.08. So that's a little bit more than a half. And from 4 terms to 8, from 2.08 to 2.71, that's more than a half. And if you look at going from 8 to 16 and from 16 to 32, in both of those cases, the partial sum grows by more than a half. But just looking at this isn't enough to tell us that that's always going to happen. Let's look at it rigorously. If we look at this, here's the number of terms followed by the partial sum at that point. If you've got 1 term, the partial sum is 1. If you've got 2 terms, the partial sum is that previous sum in this list plus a half. So it grows by a half. If we go from 2 to 4, we add on those 2 extra terms of 1/3 and 1/4. So there in red, I've got the previous sum. We had that. Then 1/3 plus a 4th. If you think about it, 1/3 is bigger than a 4th. So 1/3 plus a 4th is bigger than a 4th plus a 4th. So 1/3 plus a 4th is bigger than a half. So going from 2 terms to 4 terms, we increase by something that's bigger than a half. If we go from 4 terms to 8 terms, we're adding on those 4 terms at the end, a 5th, a 6th, a 7th, and an 8th. If you compare those two, adding 4/8 together, adding up 4/8 is a half. So the thing we're adding on here is bigger than a half. So going from 4 to 8, the sum increases by more than a half. And same thing happens going from 8 to 16. When we add on 1/9 plus up through 1/16, that's increasing by half again. So if we want to increase we can show that the sum will increase by at least a half by doubling the number of terms. So we can make the sum as large as we want to. So the harmonic series does diverge to infinity. All right, let's talk about a couple other infinite series while we're here. I want to look at each of these. 1 over 2 to the I, that's a geometric series. If we look at it, it's 1 plus a half, it's this one starting with a half, plus a 4th, plus an 8th, and so on. This is equal to 1. And that's fairly easy to see if you take there's a drawing you can do for this. If you take a square, or a circle, it doesn't really matter, and you color in a half of it, then you color in a 4th, then an 8th, then a 16th, then a 32nd, and so on. you'll eventually approach filling in the entire square. So that approaches 1. Zeno's paradox is a famous example of this. The idea is if an arrow is flying towards a target, if it flies halfway to the target, then a fourth of the way to the target, then an eighth of the way to the target, then a 16th, and so on, it will eventually hit the target, which means it went all the way. Right. Let's look at this one. 1 over I squared. Now, I've already told you that this one is finite, but I didn't give you a good explanation. If we look at the terms here, the terms are going to 0, so that doesn't really tell us anything other than we don't, when the terms go to 0, that means that it could diverge or it could converge. If we look at this running sum over here of the partial sums, those look like they're approaching a finite sum of 1.64 or something maybe, but how can we be sure? Well, there's a nice way to visualize this. These squares each have an area of 1, then 1/4, 1/9, and so on. If you look at these, the square of area 1, when you go from that to the square of area 1/4, square of area 1/4 has exactly half the length of the big square. The one of area 1/16 has half the length of the 1/4. So this little square in the bottom right corner would have an area of 1 over 64. So notice we always leave enough room on the end that we can put another square there. After that one of area 1/64, the next one will be 1 over 256. And look at the square of 1 that's area is 1/9. We could fit a square with area 1/4 up there, but we didn't. We put in a square of area 1/9. The one where it's 1/16, we could fit in more that have an area of 1/16 above, but we didn't. We put in these others. So what this tells us is if we add up all these terms, all of these areas, it's going to give us an area that's less than 2. So we know that this sum has to be less than 2. So this does converge. Now, what does it converge to? That's a much more difficult question to answer. It turns out the answer is pi squared over 6. Don't worry about trying to figure that out now. If you take a real analysis, you might see this again. But the important thing here is this one converges. All right. What about this? 1 over I cubed. Now, we already know that this one converges based on something we said in the previous section. But we can show that it converges by comparing it to this one we just looked at. We know that this converges to pi squared over 6. So if we look at each term of the I cubed series, each of those corresponding terms is smaller than the corresponding one in the I squared series. So if adding up 1 plus a fourth plus a ninth and so on gives us a finite number, adding up some smaller things has to give us a smaller finite number. So we don't know what it converges to, but we know it converges. Similarly, what about this? 1 over square root of I. This one we know will diverge, but let's look at why. Well, I should say we know it diverges because we mentioned that before, but I didn't explain it to you. Well, let's look at an explanation. If we take these and compare them, down on the bottom we've got the harmonic series, which we know diverges. If you compare these terms up top, the ones up top are larger, so they're also going to grow to infinity.